Selecting the right tyre size is not simply about choosing a tyre that fits the wheel. It directly affects the vehicle's load capacity, mobility, stability, ground clearance, traction, and durability. A tyre that is too small may become overloaded, overheat, or fail during obstacle impacts. A tyre that is too narrow can create high ground pressure, causing the vehicle to sink in sand, mud, or soft soil. On the other hand, an oversized tyre may increase vehicle height, steering effort, drivetrain load, and packaging problems. The correct tyre size is calculated by considering vehicle weight, load per wheel, dynamic load factor, required ground clearance, contact patch area, terrain conditions, speed, and obstacle climbing requirements. For military unmanned group vehicles, these calculations are especially important because the vehicle must perform reliably across roads, slopes, rocks, sand, and mud. Therefore, calculating tyre size correctly ensures that the tyre is not only strong enough to carry the vehicle, but also properly matched to its terrain, mission, and mobility requirements. Welcome to part 3 of our tyre training series, Tyre Calculations. In this video, we will cover 5 important areas that help us select the right tyre for a vehicle. First, we will understand vehicle loads, including gross vehicle weight, payload, centre of gravity, and how the load is distributed across each wheel. Next, we will examine static and dynamic wheel loads and see how acceleration, braking, cornering, and obstacle impacts can increase the forces acting on a tyre. We will then study tyre load capacity, including rated load, safety margin, and overload considerations. After that, we will learn how to calculate ground pressure using wheel load and contact patch area and why it matters on soft terrain. Finally, we will look at tyre size and width selection based on load, flotation, ground clearance, obstacle climbing, and terrain requirements. Let us begin. Let us understand how vehicle weight is distributed across the tyres of an unmanned ground vehicle. First, vehicle weight is the weight of the UGV itself without any payload. Next comes the payload. This may include equipment, batteries, sensors, cargo, or mission systems. When vehicle weight and payload are added together, we get the gross vehicle weight, or GVW. However, this load is not always shared equally by all 4 wheels. The distribution depends on the centre of gravity, or CG. The CG is the point where the total vehicle weight can be considered to act. If the payload is positioned toward the rear, the CG shifts rearward. As a result, the rear wheels carry more load than the front wheels. In this example, each front wheel carries 110 kilograms, while each rear wheel carries 140 kilograms. Together, the 4 wheel loads add up to the total GVW of 500 kilograms. Understanding this distribution is essential for selecting the correct tyre load capacity, designing the suspension, and ensuring vehicle stability and mobility. Let us take a simple unmanned ground vehicle example to understand vehicle load distribution. The starting point is the vehicle's own weight, also called the unladen weight. This is the weight of the unmanned ground vehicle without carrying any mission equipment or cargo. In our example, the vehicle weighs 300 kilograms. We then add the payload. The payload may include sensors, batteries, weapons, supplies, or other mission equipment. Here, the payload is 200 kilograms. Adding these 2 values gives us the gross vehicle weight, or GVW. Therefore, 300 kilograms of vehicle weight plus 200 kilograms of payload results in a GVW of 500 kilograms. But this total load does not necessarily act equally on every wheel. The actual load carried by each tyre depends on the position of the centre of gravity, or CG. Because the payload is located closer to the rear, the CG moves rearward. This causes the rear wheels to carry a larger share of the total weight. In this example, each front wheel supports 110 kilograms, while each rear wheel supports 140 kilograms. Together, these four wheel loads equal the total GVW of 500 kilograms. This calculation is important for tyre selection, suspension design, and overall vehicle mobility. We have now completed our understanding of vehicle loads, including gross vehicle weight, payload and load distribution across the wheels. Next, let us look at static and dynamic loads and understand how braking, acceleration, cornering, and obstacle impacts can temporarily increase the load acting on each tyre. Static load is the weight supported by each tyre when the vehicle is stationary on level ground. In the example shown, the vehicle has a gross vehicle weight of 2,000 kilograms and uses 4 tyres. We are assuming that the centre of gravity, or CG, is located at the centre of the vehicle. Under this condition, the total weight is distributed equally across all 4 tyres. The static load per tyre is therefore calculated by dividing the gross vehicle weight by the number of tyres. So, 2,000 kilograms divided by 4 gives a static load of 500 kilograms per tyre. This value represents the basic load that each tyre must support while the vehicle is standing still. In a real unmanned ground vehicle, however, the CG may shift because of payload placement, batteries, sensors, or mission equipment. This can cause some tyres to carry more load than others. Static load calculation is therefore the first step in tyre selection, before considering dynamic forces caused by movement, braking, slopes, and obstacles. G-force or dynamic loads are the temporary increases and shifts in tyre load that occur while a vehicle is moving. The first example is obstacle climbing. When the front tyre strikes a rock or step, a large portion of the vehicle's weight may momentarily act on that single tyre. A static load of 500 kilograms could temporarily increase to between 1,000 and 1,500 kilograms. During emergency braking, the vehicle's weight transfers forward because of rapid deceleration. The front tyres carry a higher load while the load on the rear tyres decreases. Depending on the vehicle geometry and braking force, the front tyre load may rise significantly. On a side slope, weight shifts toward the downhill side. This means the downhill tyres carry more load while the uphill tyres become lighter. On steep slopes, the downhill tyre load may reach 1.5 to 2 times its normal value. Finally, during high-speed off-road operation, rocks, ruts, and potholes generate sudden impact forces. These loads may be several times greater than the static load. This increase is represented using the dynamic load factor. For off-road vehicles, a factor of 1.5 to 3.0 may be considered depending on terrain and speed. For military vehicles, tyre selection must account for more than the vehicle's stationary weight. A practical design approach is to apply a dynamic load factor to the static load carried by each tyre. For many tactical UGV applications, a factor of 2 is commonly used as an initial design value. This allowance covers obstacle climbing, rough cross-country movement, rock and rut impacts, braking, cornering, suspension shock, and possible payload variation. The formula is simple. Required tyre capacity equals static load per tyre multiplied by the selected dynamic load factor. In this example, a 3,000 kilogram vehicle uses 4 tyres. The static load is therefore 750 kilograms per tyre. Applying a factor of 2 gives a required capacity of 1,500 kilograms per tyre. The final tyre selected should therefore have a rated capacity of at least 1,500 kilograms per tyre, subject to confirmation through detailed design calculations and vehicle testing. We have now completed static and dynamic loads and understood how vehicle movement, braking, cornering, and obstacle impacts can increase the load on a tyre. Next, let us look at tyre load capacity and learn how to select a tyre that can safely support these loads with an adequate operating margin. Rated load is the maximum load that one tyre can safely carry under specified operating conditions. These conditions include the correct inflation pressure, approved rim, operating speed, tyre construction, and the manufacturer's recommended usage. For example, if a tyre has a rated load of 1,700 kilograms, it means that one tyre can support up to 1,700 kilograms when all specified conditions are satisfied. Rated load should not be confused with a normal static load acting on the tyre. The engineer must first calculate the required capacity by considering static load, dynamic forces, and an operating margin. The selected tyre's rated load must then be equal to or greater than this requirement. The load index marked on the tyre sidewall is the coded representation of this rated load. It is a number that must be checked against a standard load index table. For example, a load index of 126 generally corresponds to a maximum load of 1,700 kilograms per tyre. So, the relationship is simple. The load index is the code, while the rated load is the actual load value in kilograms. Always confirm the load index, rated capacity, pressure and speed conditions using the tyre manufacturer's datasheet. Let us understand how to select the correct tyre load capacity for a military unmanned ground vehicle. The first value to check is the rated load. This is the maximum load that one tyre can carry at a specified inflation pressure and operating condition. The manufacturer's load rating should always be verified. Next, calculate the required tyre capacity. This is the static load per tyre multiplied by the selected dynamic load factor. In this example, the unmanned ground vehicle has a gross vehicle weight of 3,000 kilograms and 4 tyres. Assuming equal load distribution, the static load is 750 kilograms per tyre. Applying a dynamic load factor of 2.0 gives a base requirement of 1,500 kilograms per tyre. However, the selected tyre should also include an operating margin. Choosing a tyre rated at 1,700 kilograms provides 200 kilograms of additional capacity, or approximately 13%. This margin helps account for payload variation, pressure changes, tyre wear, and terrain impacts. If a tyre rated at only 1,300 kilograms is selected, it is overloaded by 200 kilograms. This can cause overheating, excessive deflection, reduced tyre life, and a higher risk of failure. Therefore, always select a tyre whose rated load is equal to or greater than the required capacity plus the operating margin. We have now completed tyre load capacity and understood how to select a tyre with the required load rating and an adequate safety margin. Next, let us look at ground pressure and understand how wheel load and tyre contact area influence vehicle mobility, particularly on sand, mud, and soft soil. Before we start with ground pressure, let's understand pressure first. Let us understand the two commonly used pressure units, kilopascals or kPa and pounds per square inch or psi. A kilopascal is the metric unit used in engineering and scientific calculations. 1 kilopascal equals 1,000 pascals. A pascal represents 1 newton of force acting over 1 square meter. Therefore, 1 kilopascal is equal to 1,000 newtons per square meter. PSI is more commonly used in the United States and is widely seen on tyre pressure gauges. 1 psi means that 1 pound force is acting over an area of 1 square inch. The two units measure the same physical quantity and can be converted directly. 1 psi is approximately equal to 6.895 kilopascals. In the opposite direction, 1 kilopascal is approximately 0.145 psi. For example, a tyre pressure of 30 psi is approximately 207 kilopascals. Similarly, 200 kilopascals is approximately 29 psi. In tyre engineering, kPa is generally preferred for calculations, while psi is often used during inflation and field maintenance. Whichever unit is used, always confirm the required tyre pressure from the vehicle or tyre manufacturer and avoid mixing the two units during calculations. Let us calculate the ground pressure created by one UGV tyre using the 4 sections shown. Section 1 explains wheel load. In this example, one tyre carries a load of 500 kilograms. Because pressure calculations require force, we multiply the wheel load by gravitational acceleration. 500 multiplied by 9.81 gives a downward force of 4,905 newtons acting through that tyre. Section 2 shows the contact patch area. This is the portion of the tyre actually touching the ground. Here the contact patch is approximately 250 millimeters long and 200 millimeters wide. Multiplying these dimensions gives 50,000 square millimeters, which is equal to 0.05 square meters. Section 3 calculates ground pressure in kilopascals. Ground pressure equals the wheel load force divided by the contact area. Dividing 4,905 newtons by 0.05 square meters gives 98,100 pascals or 98.1 kilopascals. Section 4 converts the result into psi. Since 1 psi equals approximately 6.895 kilopascals, dividing 98.1 by 6.895 gives approximately 14.2 psi. The key takeaway is that increasing the contact patch area reduces ground pressure and generally improves flotation on sand, mud, and other soft terrain. This image shows how vehicle weight and tyre width influence ground pressure and mobility. Vehicle A weighs 500 kilograms and uses a 200 millimeter wide tyre. Because the vehicle is relatively light, the load is spread over the tyre contact area, producing moderate ground pressure. This setup is generally suitable for roads, gravel, and firm soil. Vehicle B uses the same 200 millimeter tyre width, but the vehicle weight increases to 2,000 kilograms. The greater load is now applied over a similar contact area, so ground pressure becomes much higher. As a result, the tyre sinks deeper and mobility on soft terrain is reduced. Vehicle C also weighs 2,000 kilograms, but its tyre width increases to 350 millimeters. The wider tyre creates a larger contact patch and spreads the load over more ground area. This reduces ground pressure, improves flotation, and provides better off-road mobility. The key lesson is simple. Higher vehicle weight increases ground pressure, while a larger tyre contact area helps reduce it. Terrain correction factors help adjust the base tyre width for different operating surfaces. For highway, pavement, hard soil, and gravel, the correction factor is 1.0. This means the base tyre width can be used without change because the ground is firm and rolling resistance should remain low. For mixed terrain, the factor increases to 1.1. This adds about 10% to the base width and provides a practical balance for general military mobility. For mud and soft soil, use a factor of 1.2. The wider tyre increases the contact area and improves flotation. For sand, desert, and snow, the factor rises to 1.3. This helps spread the vehicle load, reduce ground pressure, and limit sinking or snow penetration. Peat and marsh require the largest correction, approximately 1.4 to 1.5, because these surfaces have very low bearing strength. The calculation is simple. Multiply the base tyre width by the terrain correction factor. The softer the terrain, the wider the tyre generally needs to be. We have now completed ground pressure and understood how wheel load and tyre contact area affect mobility on different terrains. Next, let us look at tyre size and width and understand how load, flotation, ground clearance, obstacle capability and vehicle packaging influence the final tyre selection. We have now understood how vehicle weight, ground pressure and terrain influence tyre selection. Next, we will study how an engineer calculates the correct tyre diameter and tyre width for a vehicle. Tyre diameter is mainly driven by two mobility requirements: the ground clearance needed below the vehicle and the size of the vertical steps or obstacles the vehicle must climb. Tyre width is selected differently. It depends primarily on vehicle weight and the type of terrain. Heavier vehicles and softer terrain generally require wider tyres to increase the contact area and reduce ground pressure. In the next section, we will examine both calculations step by step and see how these values are converted into a practical tyre size for the UGV. This image explains the two main engineering drivers used to estimate tyre diameter, vertical step capability, and ground clearance. First, consider the key rules. A practical wheeled vehicle can typically climb a vertical step equal to about 30 to 40% of its tyre diameter. Ground clearance is also commonly designed at around 35 to 40% of tyre diameter. Engineers calculate the tyre diameter from both requirements, and the larger result usually governs. Remember, vertical step height is a key factor for tyre diameter, but also wheel torque, sidewall height, traction are also to be considered during the calculation of tyre diameter. The second section explains why vertical step capability is often the primary driver. When a tyre meets a sharp obstacle, the wheel must generate enough climbing moment to rise over the edge. If the tyre is too small, the obstacle creates a severe attack angle and the vehicle may become stuck. A larger tyre reduces this angle and improves obstacle negotiation. The third section explains why ground clearance is not simply half the tyre diameter. Half the diameter is only the tyre radius measured up to the axle centre. Actual clearance is reduced by the axle housing, hubs, skid plates, suspension components, and underbody packaging. Tyre deflection under load also reduces the effective rolling radius. Therefore, practical ground clearance is usually closer to 35 to 40% of tyre diameter, rather than 50%. This example shows how an obstacle climbing requirement can be converted into a practical tyre diameter. The customer requires the vehicle to climb a 250mm vertical step. As a starting engineering rule, the maximum step height is taken as approximately 35% of the tyre diameter. To calculate the minimum tyre diameter, divide 250mm by 0.35. This gives approximately 714 millimeters. Since tyres are selected from available standard sizes, the engineer should round upward. In this case, a practical choice would be a tyre with an overall diameter of approximately 750 millimeters. The final tyre diameter should also consider available tyre sizes, wheel packaging, suspension travel, steering clearance, and vehicle stability. ISO 612 defines ground clearance as a vehicle dimension measured vertically from the supporting ground plane to the lowest fixed point beneath the vehicle. The vehicle should be positioned on level ground and the measurement must be taken to an underbody component, not to the tyre or wheel. This gives engineers a consistent method for comparing vehicle clearance. This image provides a quick rule of thumb for selecting tyre diameter from the required vertical step climbing capability. The table shows that as the required step height increases, the recommended tyre diameter must also increase. For example, a vehicle designed to climb a 150mm step may require a tyre diameter of approximately 550 to 600 millimeters. For much larger obstacles, such as 400 or 500 millimeters, tyre diameters may rise beyond 1 meter. The vehicle image shows the same principle. The tyre must be large enough to climb the vertical obstacle while still providing adequate ground clearance. Now let's move to tyre width calculation. This image explains the central idea behind selecting the correct tyre width for an off-road vehicle. The first section shows that tyre width is mainly determined by two factors: vehicle weight and terrain type. A heavier vehicle places more load on the ground, while softer terrain, such as mud, sand, or snow, can support less pressure. Together, these factors determine how wide the tyre needs to be. The second section explains this using ground pressure. Ground pressure is the vehicle load divided by the tyre's contact area. The contact area is approximately the tyre width multiplied by the contact length of the contact area. When vehicle weight increases without increasing tyre size, ground pressure rises. When tyre width increases, the contact patch becomes larger. This spreads the vehicle load over a greater area and reduces ground pressure. The key takeaway is simple. Wider tyres create a larger contact area, lower ground pressure, and generally provide better flotation and off-road mobility on soft terrain. Remember, the tyre width calculation also depends on the number of tyres a vehicle has. A vehicle with 6 tyres has more contact patch area and considerably less ground pressure compared to a vehicle of the same weight with 4 tyres. This table provides a practical guideline for selecting recommended tyre width based on vehicle class, vehicle weight, and terrain type. The first column lists the vehicle class, ranging from light recon UGV to wheeled combat UGV. The second column shows the typical gross vehicle weight, or GVW, for each class. As the vehicle becomes heavier, the recommended tyre width also increases. The next column gives the base tyre width for operation on hard soil or gravel. This is the starting point for width selection under relatively firm ground conditions. To the right, the table adjusts tyre width recommendations based on terrain. For highway or pavement, the base width usually remains the same. For mixed terrain, the recommendation increases by about 10%. For mud or soft soil, the increase is about 20%. For sand, desert, and snow, the increase is about 30%. The reason is simple. Softer terrain requires a wider tyre to create a larger contact patch, reduce ground pressure, improve flotation, and prevent the vehicle from sinking. For example, a tactical UGV in the 1,000 to 2,000 kilogram range may use 250 to 300 millimeters on hard ground, but this may increase to 325 to 390 millimeters in sand or snow. The key message is that tyre width should not be chosen only by vehicle weight. It must also be matched to the terrain and mission requirement. That brings us to the end of part 3 of our tyre training series, Tyre Calculations. In this video, we understood vehicle loads and how weight is distributed across the wheels. We then looked at static and dynamic loads, including the additional forces created during acceleration, braking, cornering, and obstacle impact. We also covered tyre load capacity, ground pressure calculations, and the importance of contact patch area for mobility on soft terrain. Finally, we discussed how to select the appropriate tyre size and width based on load, flotation, ground clearance, terrain, and vehicle requirements. Thank you for attending. We hope you found this video useful and informative. We look forward to seeing you in the next video.